Hello, today we'll be presenting the paper titled Editing Across Languages, a Survey of Multilingual Knowledge Editing. This work was done at Qatar Computing Research Institute. Large language models face a key limitation due to their static nature and knowledge cutoff. There is a need of continuously updating these models as knowledge gets outdated or incorrect over time. One approach to continuously update these models efficiently is through knowledge editing techniques. The goal of knowledge editing is to modify the factual information within LLMs efficiently without costly retraining or fine-tuning. In knowledge editing, when we apply an edit in one language, it should generalize to other languages as shown on this slide. Suppose that we want to update the fact about the President of the United States from Joe Biden to Donald Trump. The expectation is that once we apply the edit in English and the query in other languages such as Spanish, Arabic, or Chinese, the queries in other languages should also reflect the updated fact. This challenge has given rise to the field of multilingual knowledge editing, which seeks to synchronize factual updates across languages while preserving unrelated knowledge. In this paper, we present the first comprehensive survey of methods and benchmarks for multilingual knowledge editing. Specifically, we review recent advancements in the proposed MKE methodologies, the benchmark datasets that were introduced to evaluate the MKE efficacy, some empirical findings, and key open challenges and future directions towards building LLMs that are reliably editable across languages. As we mentioned, knowledge editing aims to update factual information efficiently while preserving unrelated knowledge. KE methods are evaluated across 4 dimensions. Reliability, which measures the degree to which model outputs accurately reflect the newly inserted or updated facts. Generality, which measures the extent to which the model maintains correct responses when queried with paraphrased or semantically equivalent forms of the edited fact. Locality measures the extent to which we preserve unrelated information which should not be affected by the edits, and portability measures the ability to reason about the updated facts. In monolingual settings, these metrics are evaluated on one language, while in multilingual settings they generalize to multiple languages. Many benchmarks actually were introduced to evaluate MKE methods. Please refer to our paper for more details about these benchmarks. We group multilingual knowledge editing methods into 4 categories: parameter editing methods, memory-based methods, fine-tuning based methods, and hypernetwork-based methods. Parameter editing methods modify the internal weight of LLMs to update factual knowledge. They can be broadly divided into 2 categories: general methods originally developed for monolingual settings and later applied to multilingual models, and specialized methods designed to support cross-lingual propagation of edits. Methods adopted for MKE include ROM, MEMET, Knowledge Neuron, and PMAT, while methods developed for MKE include MEMAT, MPN, LULAFNS, and MEMLA. The strengths of parameter editing methods is that they provide localized updates, thus they minimize the interference with unrelated knowledge, and they achieve efficient factual editing without requiring model retraining or fine-tuning. However, they depend on shared internal representations which are often weak or inconsistent across languages. They have limited cross-lingual generalization, and they are sensitive to tokenization and the neuron alignment. Memory-based methods, on the other hand, perform knowledge editing without modifying the model weights. We group them into in-context editing methods and memory retrieval methods. In context editing methods, we modify the model behavior by injecting factual corrections into the input prompt without changing the model weights. In memory retrieval methods, we attach an external memory to the LLM and retrieve language-specific facts at inference time. Some notable examples of this include CIRAC, Remake, MQA-KEEL, and Clever-CKE. The strength of memory-based methods is that we don't have parameter updates, thus we minimize interference with the existing cross-lingual knowledge. Edits are applied at inference time, thus which allows dynamic, flexible, and reversible updates. However, they depend on language-specific component like prompt comprehension and instruction following capability. They have limited cross-lingual propagation, and they have scalability challenges as Memory-based methods specifically incur storage and latency overheads, and in-context approaches require effective multilingual prompt design. Fine-tuning methods fine-tune the model on edit descriptors. They are divided into baseline fine-tuning, which trains directly on factual updates, and instruction tuning, which treats editing tasks as like a learnable tasks via structured instructions. The strength is that they are simple and reliable. They achieve strong factual accuracy with minimal architectural changes. We have efficient variants like the LoRa-based fine-tuning, which updates only a small subset of parameters. They are proven to have cross-lingual advances via instruction tuning methods, and specifically the XKDE method. However, other methods provide no guarantee of cross-lingual transfer. We risk interfering with unrelated knowledge, and they have data and design demands. Hypernetwork methods generate the weight updates through an auxiliary hypernetwork. And examples of this include MEND, Knowledge Editor, and Line. Their strength is that they provide this meta-learning capability as we learn to generate the edits automatically without manual parameter selection. They are fast and localized. They provide efficient, targeted updates with minimal interference with other knowledge, and they provide cross-lingual stability. However, they have a data-dependent performance. They also have a limited multilingual generalization and some language-specific constraints, specifically in the LLM method, because it relies on language-specific subspaces which can restrict the transfer across distant languages. Let's now talk about some of the findings across the literature in MKE. First, let's look at which multilingual knowledge editing methods best balance reliability, generality, locality, and portability. Parameter editing methods like ROM and MEMET work well in one language, but they struggle across languages, often causing interference. LuLaFence in particular, which is a parameter editing method, improves this by targeting shared factual neurons. Fine-tuning approaches are reliable, but they disrupt the unrelated knowledge and transfer poorly across languages. However, some methods, the instruction tuning methods like XKDE and LTE, offer a stronger multilingual generalization. Hypernetwork methods remain promising but underexplored. So to summarize, as shown in this figure, XKDE provides the best balance of reliability, generality, and locality. LuLaFence provides the strongest locality, but it has weaker portability. Parameter editors and fine-tuning provide poor cross-lingual performance. Memory-based methods have limited reliability and portability, and hypernetwork methods are promising but are still underexplored. Regarding cross-lingual transferability, it remains a significant challenge as we have many factors affecting cross-lingual propagation. One of them is the language relatedness, specifically like the family that the languages belong to, or the script that the languages are written in. Another factor is the language and directionality of the transfer, as shown on this figure, as like the language that we're applying the edit in and the language that we're evaluating on matter significantly, and multi-hop reasoning further degrades the cross-lingual performance. Regarding the impact on model size, larger and more capable models consistently yield higher editing quality, as shown on this figure. Instruction tuning further enhances robustness, and stronger models stabilize weak editing methods. Challenges and opportunities. Regarding the challenges, here we're showing three, but please refer to the paper for broader coverage. We have language and anisotropy and misalignment. As we know, multilingual LLMs encode languages and overlapping subspaces. Bridging them together is a core challenge. We have a low resource evaluation gap, as like there is a need to developing a low resource and culturally specific evaluation, and there is a need to balance the locality and the propagation trade-off. We have many opportunities, some of which are the development of robust multilingual benchmarks, language conditioned or language aware editing, and instruction tuned and task oriented editing. Please refer to our paper for more details, and thanks a lot for listening.